Welcome back, everybody. Welcome back to the channel. So today we're going to be talking about how to build our code holder. But before that, something really cool just happened yesterday. So if you guys haven't been keeping up with my commits, I was able to do this. So I'm going to say platform dot print hello world. I was able to write my first Hello World program. That's pretty awesome just to see that it's a lot of work that built up to this point to kind of get me to this position to be able to do that. So I just wanted to kind of show that really quick before we kind of get into what we're going to be talking about. So if I go back to here and I run the virtual machine, yeah, so you can see it prints out Hello World and took like 65 milliseconds. This is really cool. I'm making tons of progress on the language, so yeah. Anyway, let's get into what we're going to be talking about today. So, as I mentioned before, we're going to be talking about how to build the code holder. The code holder is pretty much the main way how we're going to store information about our program. So if I close some of these files, if you guys remember the ODF file that I've showed in a couple of my episodes, and I have like this thing where it shows the opcodes that are in the actual method that's being processed. These opcodes are controlled and manipulated by the code holder. So the code holder resides in the runtime, or no, not runtime, it resides in the grammar backend code holder. And this file is, oh, did I forget to switch over? Yeah, I did. Okay. This file is basically going to, like I said, be the main thing that we're going to use for our compiler. So here's the imports, if any of you guys are wondering. So in our code holder, we're going to need a couple different fields. So we're going to need to contain a list of units. So we're not going to get into it today because technically speaking, we really won't need this code holder for quite a while. I mean, honestly, when we're nearly about halfway done with our compiler, that's probably when we're going to use this. But I just think it's important to kind of get this out of the way first, so that way I don't have to like do more setup videos later. I like to get all the setup videos done initially, and then we can get to the fun stuff. So the format for our opcodes are going to be in the, where is it, in the runtime folder. So it's going to be in runtime. So, as I've mentioned before, I've recently transferred my programming language to support 32-bit operating systems. Now, it's not 100% ported over, but for the most part, it's in a pretty good position. So our instructions are going to be as follows. We're going to have what's called classes of instructions. Each instruction has a certain bit layout that defines what type of information that it is going to hold. And this ranges to about, what is it, 4 classes of instructions? Yeah. So right now I have about 4 classes of instructions. This is something that is set in stone. I've recently actually just changed this. Before, I think I had like only 3 classes, so I added one more. And basically the way that it works is you have what's called the main argument. So you have the argument set, and then you have the opcode. So for the first class called E instruction, or the E-class instruction, we have basically just the opcode. These are instructions that basically don't require any operands, like no op. It's just, it doesn't do anything. So it doesn't require anything. And after that, we have what's called a D class. So for whatever reason, and don't ask me why, I have no idea, but I basically, the way I structured my classes is the further away from A, the less the amount of instructions are, and the closer to A, the higher the amount of instructions. I guess the idea was that you're never going to have more than like 4 arguments, and I've yet to find a use case to basically build a bit set class that, or class A, where it basically consists of 4 arguments. I've only ever needed to go as low as 3 arguments or split it up as much as 3. So as you can see here, like for B, basically this class is expected these values to all be registers because it only goes up to a max of 127 and negative 127. The way it works is we basically have all of the bits basically allocated to a specific number, and whatever the max value of that number has, we have a plus and a minus value for each of those numbers. And we do the same thing for C class, D class, and E class doesn't really count. So this stuff's really cool. Like I said, we don't really have to go over this right now. This is more like later on when we start building our virtual machine, then we'll care about this. Also, I have a ton of just various things that I use to generate instructions. So we're going to eventually have to create stuff like masking for our opcodes, and the opcode mask is just the maximum value. So in our virtual machine, here's something I do want to mention that is extremely important that you have to consider when building your virtual machine. When it comes to generating your opcodes, you're going to have a limit to the amount of opcodes that you can generate because you want to conserve as much bits as possible, especially if you're building this to run on both 32 and 64-bit operating systems. The way it's going to work is basically we will always compile our executables in 32-bit mode for supporting 32-bit operating systems. So even if you have a 64-bit PC, we will still compile it down to 32 bits. So that way, if you port that same executable file over to a 32-bit PC, then it will also be able to be read there as well. So you just want to make sure that when you're building your opcodes, we have the minimum amount of opcodes that we need to do what we need to do. So my max is FF, and that basically turns out to be 255. So we have a maximum value of potential opcodes of 255, and that allows me to have, so 255 takes up about 8 bits, right? Am I correct? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so it takes up a byte of data, 255. That's why I picked it. And then we have the rest of the bits for all of our other information. So let's just go back to the code holder. So you're going to want to create your IR32 list, and this is going to represent our instructions. All of our instructions are going to be outputted in a uint32 format. We need to create a key pair of a list of strings and a list of code holders. Now, what these are these are called injectors, and I'm actually going to talk about that in a few minutes, but injectors are extremely important. I don't think, honestly, in my opinion, you can build a legit compiler if you don't have this code in there because building source code for compilers is a dirty ass game. It's very error prone and it's very difficult. We'll see the challenges that we're going to face later on, but yeah, you just want to create your injectors list. Do we have any other fields in here? I think that's it. Oh, we also have instance captured. So this one's a bit of a weird field. I had no idea where to put this field, so I just stuck it in here because it's technically related to the code, and basically what this represents is as we're processing data, we're going to be like, if we say, this field dot this field dot this field, we want to, the way that I'm going to basically generate code for processing every single field and processing code, I'm going to always assume that we don't have the instance of the thing that we're processing. Meaning that if you say you want to access field X, then I'm going to attempt to get the instance that field X resides in to then go and access field X. So we need this instance captured variable to basically say, in this code base here, have we already captured the instance of the field that we're trying to access or the thing that we're trying to access? So let's just kind of look to see what are some of the functions. So we're going to start out with a basic constructor. We're going to create our code holder and call init. All this does is it just sets up our values. We set up our IR32 list and we set up our injectors and we get the key and the value and initialize those because if you remember, these are two lists inside of this key pair. So we just access the key and the value and initialize those lists. So here's kind of how injectors work. So basically the way an injector works is I'm actually going to go to, what is it? utype.cpp. So if I go to utype.c++, and up here you can see I have a bunch of strings that represent injectors. The way injectors are going to work is we're going to have the name of the injector, which is going to be represented in the code holder as the left side, or I think this is like the key side of the key pair. And then we're going to have the corresponding code holder for that injector. And the idea behind that is that we have an injector that is basically going to hold a certain amount of code with the name attached to it. So if we want to say, I want to get the stack injector, that means that the code inside of this injector is going to pertain to getting values and pushing them onto the stack. So that's kind of how it kind of works. So if we go to adding an injector, if we want to add an injector, first we need to check to see if we do not have the injector. So we check that by just for looping through our injectors. We for loop through the keys. So we say injectors.key size. We for loop through the keys, and then it checks to see if the key matches the value. If so, we return true. We go back up to the top. So that's how you add a injector, and then so once we determine that we don't have it, we basically just create a new value inside of the list, initialize the value, because we want to initialize the value, which represents, which represents the code holder, and then we want to initialize the native string as well. So we call init on both, and then we basically just set the key. So we get the last value of the name. So if we go and get the key, which is the string or the name of the actual injector, we assign the name based on whatever we passed in. And then we return true if we've successfully added it. Otherwise, we return false if we didn't add it. After that, you want to be able to add a value. So like if we want to add an I32, which is basically just an instruction. So an instruction 32, we basically pass in the injector that we want to add this instruction to, and then we check to see if we have that injector. If so, we get that injector, we get the instruction list, and then we add the value. Oops. And then of course we return true, otherwise we return false because this returns a Boolean. After that, you want to be able to add IR. Now, here's something that I think I should mention. So if we go back up to the opcode, there's going to be a couple different ways that we process instructions. So, or there's really only two ways. So of course we have our bit layouts, but there's what's called, and I'm just going to make up this right now, there's what's called single based instructions and binary based instructions. And I just made up that name, but basically what that means is not every single instruction is going to be 1 byte wide, so or one instruction wide. So each instruction is going to be, as I've mentioned before, 32 bits wide. And basically the binary instruction that I'm talking about is two of those 32 bits wide. So if we look at this int instruction, we can see that it uses the setDi, which basically denotes that this is a class D instruction, meaning that it only has one argument. So if we go back, that's for int. But as you can see down here for movi, it's two arguments. So we create what's called an instruction buffer. And again, we're going to go over this code later, but an instruction buffer is just a array of opcode instructions, which this is just another word for saying unsigned int because that's going to be the format of our instructions. And an opcode arg is going to be an int. So if we go back, we can see here that in order to create the move I instruction, which basically means move an integer, move this integer value into this register. So we move this value into the out register. And we basically pass in the first set of parameters for the instruction. So we pass in the D class version, and then we pass in the value. And the reason why it's like this is because when we're assigning integers to, let's say, I don't know, a local variable, right? If we're going to use this move I instruction, we want to be able to assign the full width of a 32-bit integer. So if we have a constant of a 32-bit integer, we want to pass that value into here so that we can contain the entire value. If we were to use the di instruction, each class or di class for the instruction generation, each class has limits. So even di, which is the absolute largest instruction where you can pass an argument to, D class instructions have a limit of, what is this, like 8 million? Yeah. So, and also this is going to play a part in how we compile our code, right? Because obviously nothing is infinite when it comes to programming. And so basically, since we have these classes, we'll go over this later on, but that's going to limit how much of a thing that we can process be processed. Meaning that, let's say, I don't know, for accessing strings, we use the class D instruction for accessing and manipulating strings, then we can have basically a maximum of 8 million strings. And of course, if we use any other instructions, we could have a maximum of 200,000 or 262,000 of whatever we're processing. So just kind of keep that in mind when we are coding and, as you're building your programming language. But if we go back to adding an IR, we can see that this is a single instruction that we're passing in. So we're not passing in two values. So the assumption is that all of the data that we need to process this instruction is going to be packed into this integer. So we just call pushback and we push that to the end of the list. After that, we return this. Now, the reason why we want to do that is because it allows us to basically chain a bunch of add IR calls together, and it looks very clean. So if I go to compile, we want to be able to do that. As you can see here, like here's an example, right? So compiling an array expression, I have some code down here where I'm basically, I'm basically getting the code of this U type, and I'm adding a bunch of IR or intermediate representation code. And I'm just chaining a bunch of calls together, and that's kind of how that works. So we want to be able to do that to just make our code look nicer. Of course, we have all of those fields, which we went over. Now we have a free. So free, we also want to return a reference because we do chain method calls after this as well. So if we want to free up, we just free up, our instructions, we free up our keys, we go through and we free up each individual value because values are in fact code holders. So we need to go through each code holder and individually free each code holder. And then we of course can free up the total list of code holders after that. And we set instance captured to false. And then after that, we return the current instance. After that, we have free injectors. So in order to free up all of our injectors, we just want to go through our list of injectors here, and the value represents the cold holders, and we basically just free up those cold holder values. We free up that list, and then we free up the keys. After that, so now we have an instruction buffer, and as you can see, I have in my opcode file a thing called op builder. Now this is going to be, as you can see, here's actually all of my instructions. So this is like an init opcode define statement where I list out all of my instructions, and as you can see, I have a ton. But what's important is that this op builder class that I created, this is, and you're going to see this throughout my programming language, you want to build a bunch of low level and high level fail safes. So the way that this system is going to work is as we're generating instructions, I made this mistake before, but I used to, and in fact, I can actually go to my old compiler. If I go to, where is it at? Old grammar and then runtime, you can see I have a set underscore ci. So as you can see here, like I just went to a random spot in the code. This is me generating instructions. This is very dirty. First of all, I'm not chaining the method calls, right? So I have to call block.code every time I want to add an instruction. But not only that, even worse, I have to basically remember for every single instruction, wait a minute, what was the bit layout for that instruction again? I don't remember. So I ended up having to copy and paste a bunch of instructions from other spots where I basically outputted that instruction, and it just wasn't a very clean way of doing it because it caused tons of bugs. Like if I set this move I instruction as a C class instead of a D class, well, the virtual machine is going to expect this to be in the D class format. And if I made that mistake, obviously that's a problem. So in our op builder, in our opcode, we're going to have that pointer. We're going to return basically a pointer of opcode instructions. And we basically know that the maximum amount of instructions that we could process is 2 because that's the limit. So I have a couple of instructions that use this instruction buffer. And the max width of every single instruction has always been 2 instructions wide, so that's the assumption there. So with that being said, it's safe to assume that this pointer is going to be 2 N32s or UN32s wide, so we can just basically say the buffer size is 2, we go through the buffer size and we add the IR. And then of course we return the current instance. Now this is really cool because what that allows us to do is compile and generate both single instructions where we just pass in one integer, and then double instructions where we pass in, multiple integers. And as we're kind of processing our code, we don't have to care about what the format is for our instructions, like move r, checklen, pop object underscore 2, or pop object 2. We don't have to care whether or not this is 2 instructions wide or 1 instruction wide. So it's really nice to just have everything kind of work harmoniously like that. After that, we have remove in. So we want to basically pass a count of how many instructions we want to remove, and we want to remove those instructions off of the end of our cold holder. That's very important for later on when we're processing getters and setters. So that's kind of what this function is used for. So we just have a while loop here where we say, while the IR32 list is greater than 0, we continue to decrement the count, and we just continue popping back until count is not equal to 0. Otherwise, if it's equal to 0, we break and we return the instance. After that, we have inject. So here's an example where we want to inject a assembler or another code holder at a specific index. So if we want to, let's say, inject some code at index of 55, we can easily do that by calling this and passing in a code holder. And I use this a lot. We're going to see this being used a ton later on. So all we need to do is just check to see if I is less than 0. If so, we set our start, then we return. Otherwise, we're good to go. So we basically just say we want to start at I. We have an iter, which is basically just keeping track of how many times we've iterated. And we need this because we want to start, like the assumption is that we're injecting these instructions at this index, but those index values are going to be two separate things, right? So if we're injecting values at index 5, well, this assembler might have 5 instructions. So we want to start at 0 and plus plus up, so that way as we're putting all of our code in, we can continue to access newer instructions from incrementing the iter variable. So after we do that, then we want to inject an entire assembler. So it's kind of the same code. All we do is just say we want to start at the size of our current IR32 list, which is basically just the end of the list. So we're just basically tacking on the code from this code holder to the end of whatever we have. We set our iter to 0, and we run the exact same code that you saw above. After that, we have, so here's an example where we want to just directly inject an injector that we already have in the current cold holder. So we basically say get injector, and we start again at the very end of our list, and then we set our iter to 0. And then after that, we do the same code as we've done above. So that's pretty similar. So yeah. After that, you want to get the size of our code holder. So, what is the size of the list? You want to be able to get an injector by just for looping through our keys or our strings. We check to see if the string value at I is equal to whatever the name that we passed in. And what we pass is the value. So we don't pass the key, we pass the value because we want to get the code holder that is in reference to that name, basically. So we're going to have to make sure that our keys and our values are always staying hand in hand together so that we can process things properly. Otherwise, if we don't have the injector, we immediately add the injector, and then we just simply return the last cold holder. So this is going to be really useful. We use this in a ton of spots too. We also have copy injectors. So what this is going to do is it's going to free up all of our injectors, and we're going to for loop through all of the keys that are present inside of this cold holder that we passed in, and we're just going to get the injector and inject the value. Now, if you remember, get injector, if we don't have the injector present, it's going to add it. So this basically guarantees that we can basically get all of the injectors based on the name values that are inside of this cold holder, and then we just inject all of the code from the functions that I showed you above. After that, we have remove vector. That's not really used, but basically we just for loop through all of our keys. We look for the name of the injector that we want to remove, and we remove both the cold holder and the respective key at the same position, and then we just return. After that, we have has injector. Yeah, so that's kind of it. So that's going to be it for today. We've pretty much gone through everything now at this point. So we're now ready to start building the compiler. Now, I just want to say something very important. I've been working really hard for you guys to make sure that I can continue this video YouTube series, and literally almost every time when I upload a video, I just finished code like literally hours before I filmed the video. So, with that being said, though, I've made tons of progress, and at this point now we're at a pretty decent point where I've gotten through all of the heavy lifting that we needed to get through. So we finished the parser and we've set up all of our code for our compiler, and now all we just need to do is compile it, or I need to show you guys how it's compiled. So I'm going to start going back to my regularly scheduled programming as of tomorrow. So I'm going to put out a video tomorrow kind of explaining what are we going to expect from this YouTube series. It's going to be a pretty interesting video. I'm going to be answering a question that I got a while back, kind of explaining where somebody basically said, they're just now getting into C++ and they're not sure if whether or not they should be building this programming language now or should they wait and like learn more C++. So I'm going to be going over that question as well, and I think it's going to be a pretty interesting video. So hopefully it'll answer you guys' questions. And I'm sure just like you, whenever I watch a tutorial, I like to know what is the end product result of what I'm going to get from the tutorial before I go and spend all my time watching the tutorial. So that's kind of the purpose for tomorrow's video. I think it's going to be very valuable for you guys to kind of just get a transparent view as to what we're going to be learning, what we're not going to be learning, because there are some things that we aren't going to be learning as well. And yeah, so we'll see that tomorrow. So after tomorrow's video, we're going to be going back to our regularly scheduled programming of Monday, Wednesday, and Friday. And after Thursday, I'm not going to be uploading a video on Friday. If I'm being completely honest, I kind of need a little bit of a break. I've been working really hard on this language, staying up until like 2 to 3 in the morning, getting like 2 or 3 hours of sleep, and I've been doing that for the past couple of weeks. So, I'm going to take a little bit of a break. Hopefully, you guys can understand. But don't worry, because like I said, I'll be back on Monday and we'll just continue the YouTube series and start getting into compiling everything. So, as usual, if you guys have any questions, definitely put them in the comment section below. Also, if you guys would love to help support the channel, definitely head over to my GitHub repository at androdevcd/sharp. And when you do, definitely watch, star, and fork this repository. That's going to give this repository a lot more visibility and let other developers know this language exists. Also, if you're curious about learning maybe what I've been up to on a day-to-day basis, you can check out the remastered branch. This is pretty much where I do my day-to-day development in the language. And you can check out the commits. Now, I've been writing some pretty lackluster commits, but typically they're pretty wordy and you can kind of get a gist of what I've been up to without really having to look into the code. Also, if you're curious about learning maybe stuff that I'm looking to add in the future for this YouTube series, or maybe stuff that I've worked on in the past, you can head over to the docs folder. And in there, there's going to be two main files. You can check out the changelist file. That contains everything that I've done in the past as far as updates and releases for the language itself. And the roadmap file contains not only that, but it also contains things that I'm looking to add in the future. So that's going to be it for today, guys. As usual, if you guys are new to the channel, definitely consider subscribing. And until next time, I'll see you guys later.